Well, it's 11 o'clock. It's only 7 of us here. Okay. Interesting. How are y'all doing today?
Doing good. How are you?
Doing okay. Doing okay. So I sent out the review, but last week sometime. I sent out the solutions, I think, yesterday. So the exam that we're going to have for covering everything up through 5.4, 6.6 is not going to be on the exam. That'll all be, or that exam will be on Wednesday. So, all right. Are there any questions before I begin? We need to kind of wrap up the chapter 5 stuff, 5.2, 5.2, 5.2, 5.3, 5.4. Anything? Any questions? All right. All right. See, this is always my fear of giving a review out, is that people get the review and then they don't come to class because they're like, oh, okay, well, I've got what I need. You know, I'll just work on this. So, okay, it is what it is. So today we are going to finish up what we had started last time, and that is, you know, we had started with this idea of the area, right? The area problem. Area of a circle, and then we did this idea of trying to find the area underneath the curve, and we went through this big old long drawn out thing, and I apologize because I was really rushing to get through this. And after everything was said and done, we got to a formula, and this is the formula we got to, that if we want to know the area underneath the curve, a function f, and we cut it up on some interval a and b, and we're trying to find that area between that function and the x-axis, that we're going to cut it into n rectangles. And after we cut it into n rectangles, we're going to take the limit of that and let the number of rectangles go to infinity. Let n go to infinity. Now, to actually calculate that by hand is very difficult to do, all right? In general, if somebody hands you a function and asks you to evaluate this thing, very tough. Now, we can try to do it, and there's some formulas that we would need for sums that I'm not going to cover. I've decided I'm not going to get into the calculation of Riemann sums by hand, because they're, like I said, they're difficult, but then they're time consuming, and at the end of the day, we have the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus is what saves us from having to do this calculation. So I'm just going to get to that fundamental theorem of calculus. The evaluation theorem is what it's referred to as. And it just says, hey, look, if you've got a function that is continuous on a closed interval a, b, then this symbol, this right here, this notation now represents that limit of the sum. It's all all those rectangles added up. That's now the notation for it. And what it's equal to is just the antiderivative evaluated at the two endpoints. I mean, this is a major deal. It says that, you know, if you want to know about the area under a curve, all you have to know are 3 things. You have to know what the antiderivative of the function is, and then you have to know the 2 endpoints of the interval, and that's all you need. If you have that, you can find the area underneath the curve, which is remarkable, but that's why it's called the fundamental theorem. It is fundamental to what we're doing. So we're going to do some examples. And note here it says this is called the definite integral. That's what this is referred to as, the definite integral. Because what's going to happen is when we have a definite integral, we have these numbers that we put here on the integral symbol. We're now going to have an answer that is a number. Whereas before, we always had an answer that was a function plus a constant. With definite integrals, you're always, well, not always, if the limit exists, you're going to get a numerical answer. So it represents area, right? So we call that the definite integral. as opposed to what we were doing before, which we refer to, this is what we were doing before. That's called the indefinite integral, all right? So let's do some problems. I'm gonna do this first one here. I'm just gonna move this to a different window and I'll copy it over here. So the first one we're gonna do is the integral from 1 to 2. So those numbers here are called our limits of integration. This is called the lower limit of integration. And the top one is called the upper limit. But all those are the endpoints, right? Those are just the endpoints of the function where you're looking. And what we're going to do is this function here. So 4x cubed minus 3x squared plus 2x dx. All right, so let's find the area underneath that curve between 1 and 2. So if we were able to graph this, which I'm not going to graph it, but we have some curve. We're looking between 1 and 2. The function does something, we're not quite sure, but we're going to find that area between the function and the x-axis. And to do it, all we do is first find the antiderivative. So we're going to just write the antiderivative down, which is just x to the 4th minus x cubed plus x squared. We're just using power rule, right? And then we're going to put this line here. We'll put this line here. That's called the evaluation bar. And we're going to put 1 and 2 here. And all that does is reminds us we still have something to do here. We still have work to do. We've got that now equals, and now what we're going to do is the f of b minus the f of a. Okay, that's the fundamental theorem. And I like to always just put 2 big sets of parentheses. And then I'm going to just plug my numbers in. So I'm going to plug 2 in for x first. You always start with the upper limit of integration. That's your b. So we plug 2 in there. What do we get? 2, 4, 16 minus 8 plus 4. And then we plug 1 in, which gives us 1 minus 1 plus 1. So what do we get there? 8, 12. And then take away from that 1. So we get 11. So the area is 11. Notice that the area is just it's given to us as a number. There's no units associated to this. So it's not like 11 square feet or 11 square inches or 11 square miles. That would have to be given to us in the context of like a word problem. If we somehow had values here given to us, then we could actually put some unit onto that numerical answer. For us, our answer is just going to be a number, all right? Later on, it could have some other meaning, but for us, it's just a number. Okay, so that is it, and I'm going to show you what this graph looks like. So if we were to actually graph this on a graphing calculator, here's the function, and we're looking just between 1 and 2, and we calculated that that area is 11, which is kind of weird. I mean, it's kind of odd that we got a nice number, 11. That just is because of the way I picked the function, everything worked out nice. In general, I wouldn't expect to get nice answers like that. Okay, let's do the next example. Are there any questions? Can you all see how this is pretty much just same stuff we've done? We're just adding one more step to it. Okay, how about this?
We don't add a constant when we take the derivative of this on?
Good question. Okay, let me go back to that one. So here's the deal. Let's just say we had added plus c in here. Okay, let's just say we had added plus c in there. Then when we came over here, we would have plus c and we would have plus c here also, right? And then when you do the subtraction, this minus would distribute through and become a minus c, and it would kill off that c, wouldn't it? And that would happen every time, no matter what. So when we do definite integrals, we will not put the plus c here. We will not put that there in front of that evaluation bar. We don't, I mean, you could, but it's going to go away anyway. So just you may as well not write it. Good question. Okay, so the next one I want to do is 5x minus 5 to the x plus x to the 5th. and we're looking between 0 and 1. I'm going to graph that real quick, all right? Because I just kind of made up this problem on the fly here. So 5x plus 5 raised to the x plus x raised to the 5th. So there's our graph. Okay, here's our graph, and we're just looking between 0 and 1. So if I put here, if I put here, see if I remember how to do 0 less than or equal to x less than or equal to 1. There we go. So there's the graph of that function just between 0 and 1, yeah. Okay, and we're trying to find the area below that. So we're trying to find this area in here, okay? All right, so to do this, we need to be able to find the antiderivative. So let's go and try and find the antiderivative first. So the antiderivative of 5x, we can do these individually because we have addition and subtraction. The 5 comes for the right. The antiderivative of x is 1/2 x squared, so that'll become 5/2 x squared. Let me do the last one because that one most students will be okay with, plus 1/6 x to the 6th. What about this one though? 5 raised to the x. So I see some people looking at their formula sheets. That's good. If you go to your formulas, we have formula number 5 is how you take the antiderivative of a number raised to your variable. So we have 5 raised to the x. So our antiderivative should be 5 to the x divided by the natural log of 5. Okay, so just be aware of that formula. You should kind of recognize that from Cal 1 because you do take the derivative of that in Cal 1. Okay, so this is going to be minus 5 to the x over natural log 5. And now I just need my evaluation bar, 0 and 1. I like, again, 2 big sets of parentheses. And let's plug 1 in first. So we just get 5/2 minus, let's see, 5 to the 1 is 5 over natural log 5. And oops, I forgot my plus sign here, plus, and then that's just 1/6. And then when we plug in 0, be careful, we do get 0 in the first one, but the second one, 5 to the 0 is 1, right? So just be careful with that. That's going to be 1 over natural log of 5 and then plus 0. So 5/2 minus 5 over natural log 5 plus 1/6 minus 1 over natural log 5. And I could put these two together because they both have the same denominator. I'm also going to join these together. So I get a common denominator there. Let me see, what do I get there? 15. So I think I get 16 over 6. Is that right? Minus 6 over natural log 5. I can reduce that to be 8/3.
Real quick, would the minus 1 natural log of 5, would that be a plus? Since we would distribute the...
Oh, yeah, sorry. I didn't put my minus through there. Yes, plus. Thank you. So that would actually change that to a 4. Thank you. Minus 4. And that would be the exact answer. We could just leave it like that. Now, if you want to get it on your calculator and get a decimal, you could. Just to finish it off, just so we have an idea of what this area is. I think I got that all in there. It's approximately 0.181. That's what I'm getting. Yes? Okay, let's look at the next one. So this one is interesting. Let's go from 0 to 2 pi sine x dx. All right, so before, we're not going to look at the graph. We're just going to go straight to it. What's the antiderivative of sine? Antiderivative.
Is
Negative
it negative cosine?
Negative cosine. Evaluating from 0 to 2 pi. Okay, so we're going to have two things we're going to subtract. First, we plug in 2 pi, so we get negative cosine 2 pi. And then we go negative cosine of 0. What is cosine of 2 pi?
0 or 1, my bad.
1. Okay, so that becomes negative 1 minus over here, negative, okay, cosine of 0 is also 1. So we get, what is that, negative 1 plus 1? We get 0. We get an area of 0. Now let's take a look at the graph. We were looking at the sine function, right? The sine function looks like this. And it has a period of 2 pi. So we were trying to find the area underneath this from 0 to 2 pi, and we said that the answer was 0, which is kind of odd because that means that it's counting this as almost like a positive area, and it's counting this over here as like a negative area. So this definite integral is not giving us like a true area, it's giving us what we refer to as the net area. And it's counting everything below the x-axis as negative area and everything above the x-axis as positive area. And that's just the nature of the beast. Now, let's try and understand why. Remember that when you're looking at this definite integral, one of the most important things that I wanted you to take away from this was that each part of this definite integral has meaning to it. F of x, if you go back and look at your notes, represented the height of each of those rectangles. And the dx represented the width of each rectangle. And the integral just represented the limit of that sum, right? So this notation means, hey, look, we're going to look between A and B. We're going to add up an infinite number of rectangles, or I should say, we're going to add up an infinite number of things. And the things that we're going to add up are these heights of these rectangles times the widths of the rectangles. So that's your area, right? Those two multiply gives you the area. But that height is completely controlled by the function's value, right? So if you're talking about rectangles over here, then of course the height of those are all going to be positive heights, positive height, positive height. And then the widths are always positive, widths positive, widths positive. So when you multiply two positives together, you get positive. But when you get to the other side over here and you start looking at these rectangles, right? Your widths are all positive, but your heights, because they're the function's values there, are going to be below the x-axis. These are all negatives, right? This height here is negative. This height here is negative. So when you multiply a negative and a positive together, you get negative. So that's why it's counting, it's subtracting that from the total sum. I hope that that makes sense. Now, one thing we could do in order to figure out what the true total area of this would be to do the following. We could change our integral and we could go from 0 to just pi, right? If we went from 0 to pi, then that should give us just that first piece, right? Just that piece, that area. And then we could say, oh, okay, well, if you double it, that would be the total, if you wanted the true area. So the only difference between that is, same antiderivative. Now we go to pi, so we plug in negative cosine of pi, and then negative cosine of 0. All right, so this becomes, what is cosine of pi? So cosine, unit circle, go over at pi, the x coordinate is -1 there. So this becomes -1. And then minus, let's see, negative cosine of 0, we already said was 1. So what do we get here? This is 1 plus 1, that's 2. I've always found that to be extremely weird. That if you wanted to know what the area is under one of the arcs of the sine function, the answer is 2. I've always felt like it should be like some weird decimal or something, or that it should have some like pi involved. It just as though it never made sense to me that that should be just a nice number, but it is, okay? It is. So we have to be careful when we're dealing with these definite integrals, you know, what's being asked in the problem. Are they asking for the net area? Like in this first problem we did here, like this, where you're gonna give the answer will be 0, that is the correct answer. Or are they asking for more of like a geometric total area? And if it's total area, you have to know what the graph looks like a little bit in order to determine like where to start and stop your integral so that you can pick up that positive part, you know, on that little piece. Now, I wouldn't worry about that for this test. For this test, we're just going to do the net area, and that's all we're going to be concerned with, all right? The next test, we might have to investigate the function a little bit more before we can get an answer. Okay, let's do another one. Okay, how about this one? How about the integral from 0 to 2 pi of x squared cosine x dx? Let's look at it first. I'll graph it first. It was x squared times cosine x, and we want that from 0 to 2 pi. There it is. There's the graph. All right, so what we're trying to find here, let me see what I can do here. Hold on a second. Let me change this to 10. There we go. That'll work. So there's our graph. I'm going to bring this over here, copy it. So what we're trying to do is find the area here, the net area, okay? Not the total area geometrically, but the net area. So what we should expect is that we're going to have, let me see, I'll do the area under here. It's going to be hard for me to do this. I'll do it in green. This little area right in here should give us some positive contribution to the area. Then we're going to have the area here, which is going to give us some negative contribution. And then when we stop at 2 pi, which is about there, we're going to have this area, which is going to give us some positive contribution. We are not going to look at each one of these separately. We're not going to figure out what this one is and this one and this one. We're just going to look at the net area, okay? If we had to figure out the total area, we would actually have to figure out where these things start and stop. So I would have to go figure out what's that x-intercept? What's that x-intercept? Which means I would have to take the original function and set it to 0 to find the x-intercept. And so I'd have to go solve that equation. We're not doing that, okay? We're just going to look at the integral and find the net area. Do y'all think we're gonna get a positive answer or a negative answer? Do you think there's more positive here than negative, or more negative than positive? Or do they wipe each other out and become 0? I don't know. We have to see, right? I mean, you might have it, you might think it's positive. We don't know for sure, all right? So we've got to do the actual problem. So 0 to pi. How are we gonna find the antiderivative? We have to find the antiderivative x squared cosine x.
Would it be integration by parts?
That's right. So what we're going to have to do is, we're not even going to work on that problem. We're going to go back to an indefinite integral to start, because now we realize that the antiderivative is going to take some work. So I'm going to do it as its own problem. So I start here, do integration by parts. What am I going to choose for u, and what am I going to choose for dv? What do y'all think? What would you choose for u, and what would you choose for dv?
I don't know if this is right, but for you, I'd pick x squared and dv to be cosine x.
Yeah, that's a good choice, because what will happen is that in the first step of integration by parts, you're going to have that x squared is going to come down and become a 2x. And so the power went down, right? When we do the antiderivative cosine, we just get sine. So that's just going to switch from cosine to sine. So that's not a big deal. And then we do ultraviolet minus voodoo. There's ultraviolet minus the integral of voodoo. And voodoo is this times this. I'm going to bring the 2 out, and I'll still have their x sine x dx. So now we look at that integral, x sine x dx, integration by parts a second time, right? We're going to need a second iteration of integration by parts to do this. So this right here, I'm going to do that with another integration by parts table. I'll go u is x, dv is the sine x dx, du is dx or 1 dx, v is negative cosine, be careful with that. Antiderivative of sine is negative cosine. And now I'll have another ultraviolet minus voodoo, right? So this becomes x squared sine x, that was there already, minus 2 was there, and then now in brackets, my new ultraviolet minus voodoo. There's ultraviolet. Oh, shit. Do y'all see I put a dx here? Right there? I have no idea why I put a dx there. Why did I put dx there? No idea. Okay, so this should just be negative x cosine x minus integral. Okay, now again, we do voodoo, which is this times this. I'm going to pull the negative out, right? That negative there on the voodoo, I'm going to pull the negative out. And that should change that minus to a plus here in red. And then the only thing left in the integral is just cosine x dx. Close my bracket. And I think at this point we're ready for our final version here. Let me see, minus x cosine x. Antiderivative cosine is just sine, so plus sine x. Now over here we would say plus c because we're doing an indefinite integral. Is this good? So now I'm going to come back over here and I'm going to say this is equal to, and now I'm going to write that down, x squared sine x. I'm going to go ahead and distribute this negative 2 through. So we get positive 2x cosine x, and then minus 2 sine x. And that's the antiderivative. Evaluation bar 0 to 2 pi. This should equal something minus something. So what about plugging in 2 pi? So let's see, we have 2 pi goes into the first one, so 2 pi goes in for x, that's squared, times sine of 2 pi, plus 2 times 2 pi times cosine of 2 pi, I'm going to run out of room, minus 2 sine of 2 pi. Now, what is sine of 2 pi? So you have to kind of know that, right? Sine of 2 pi, 0, so that's 0. That one is 0. That kills all that off. Okay, so all we have is this piece here. We've got the 2 pi. What is cosine of 2 pi? We've done that, right? That's just 1. So what does all of this turn out to be, this first piece?
4 pi.
4 pi. Okay, and then we still have minus. Now we haven't done this one yet, minus. Okay, over here we're plugging in 0, right? What happens when I plug 0 into all this? Isn't everything gonna go away? Like that'll go away because it has an x squared out front. That'll go away. And then when I plug 0 in for sine, sine of 0 is 0. So all that is going to turn out to be a 0. So our answer is 4 pi. All right. What do y'all think? Integration by parts with a definite integral. All right, let's talk about some properties of definite integrals. So let's go through these properties one by one. The first property, I want you to think about this. If I want you to do the integral from a to a of some function, what do you think the answer should be?
Be 0, right?
0, okay? Because this is asking you to look at a function. It's asking you to start at A and end at A and find the area. Well, if you start at A and end at A, then you're only talking about like that single line segment straight up, and a line segment does not have an area. You have to have some width. And so this should be 0. That makes sense? Okay, the next one is a little bit harder. The integral from A to B of some function should be equal to, well, I don't know. You tell me if you think this is equal. Do you think that those are the same? Do you think that the integral from A to B is equal to the integral from B to A? So it's kind of like if I have an,
Yes.
when I go from A to B, right? And I want to know that area. Is that the same as the area from B to A? Seems like maybe it looks like the area would be the same, but it all has to do with when you think about geometrically the way the rectangles are drawn. Okay, so when you have B and A backwards like that, then instead of going from left to right, okay, so like on this integral right here, what we're doing is we're moving from left to right as we're drawing our rectangles. So we're drawing our rectangles from left to right. So each of these little widths is positive, positive, positive. But if we go backwards and we go from B to A, so on this one we're going, on this one right here, we're going to go from right to left. Then we're starting our rectangles here and we're drawing this way. Then each of those are now negatives. And they're negatives because when you try and do that piece, I don't know if you remember on our formula that had the sum in it, we had that last piece, the width of each rectangle is B minus A over N. That was our width. So if we go backwards, that's actually going to become A minus B over N. And A minus B will be a negative number each time. And so what happens, you get negatives as your width instead of positives. So the relationship between these is that the sign changes. This becomes negative. So the area from A to B underneath the function is equal to the opposite or negative of the integral from B to A. So if you switch the order, of integration on an integral, all you have to do is put a negative sign out. Okay, that's all this is saying. Switch the order of integration, then change the sign. Third one. Okay, what do you think the integral from A to B of a constant is? So I'm using K here for a constant instead of C. Normally we use C, but We've been using C whenever we do like an antiderivative plus C, so we're just using a different letter for a constant. So what do you think that the area under that would be? So let's look at it geometrically. You have a function. You're going from A to B, and your function is a constant function, right? So it's flat. And it passes through at K, right? That's where it passes the y-axis. If you want to know this area, well, that's just a rectangle, isn't it? How tall is the rectangle?
Okay.
Okay.
Right, that's K. And how wide is the rectangle?
B minus A.
B minus A. So this should just be K times B minus A. So as an example, okay, let's say we want to know the antiderivative from 2 to 5 of 3 dx. We wouldn't have to do any work here. We would just say this is 3 times what?
5 minus 2.
5 minus 2. That's 3 times 3, and that's 9, right? Now, even though that formula or that property is nice, if this were me, I would just, this is not a hard problem. The antiderivative of 3 is just 3x. And then I could put the evaluation bar here. And now I just plug in my two numbers. So I plug 5 in there, I get 15. I plug 2 in there, I get 6. And if I subtract that, I get 9 still, right? So it's not like that property is saving us a whole lot of time. It's like we have to still remember the property. It's not that bad to actually just do the antiderivative, right? So it doesn't matter which way you do it here. Both ways will give you the same result, but it is a property. All right, how about this one? This next property is obvious, I think, because we've used it so many times. If you have a constant in front of a function that, I'm just going to tell you what this property is, and then you'll be like, oh yeah, that makes sense. Just like we had with indefinite integrals, we always said constants could come out, right? That's exactly what this fourth property says. If you have a constant in front of a function, then what you can do is you can bring the constant out, and you can just go find this. Find the area of the function without the constant, and then just scale it by whatever the constant was. Fifth property. This one's a little interesting. Let's say that I tell you this about a function. So what is that statement saying to you? If f of x is greater than or equal to 0 on AB, what is that telling you? That function is what?
Positive.
Positive, or it could touch the x-axis, right? But it's never negative. So if you have a function that's always above the x-axis or maybe touching the x-axis, then what can you tell me about the area underneath that? It always would have to be positive, right? Or possibly 0. So if the function is always above the x-axis or touching it, then you know that the area underneath it will always be positive, or at worst case, it could be 0. And then property 6 is the opposite of this. Property 6 is just if you have a function that's negative or potentially 0 on some interval AB, then of course the integral, the area below that function, should also be negative or possibly 0. And that just comes from the geometry, right? Function is above, that's counted as positive. Function is below, it's counted as negative. Any questions on those? These are all in your notes, by the way. I believe this should be in Canvas under notes, these properties. All right, so that we have three more properties. The next one, property 7, says this. I'm going to draw it first. It says, let's say you have a function from A to B here, and you're interested in that area, okay? So you want to know what the area is underneath that function. Says that this property says that if you come in here and you pick any number you want, doesn't matter where it is, pick some value in here, we'll call it C, all right? It says that this area, the total area under everything, would be equal to the area from A to C, whatever that is, plus the area from C to B. So this property says that you're allowed to break up the total area into parts. You could do this piece with that integral, and then you could come and do this piece with that integral and add them together. If you add those two together, that should give you the area of the whole thing, which is what maybe you were interested in the beginning. So it just allows you to split up an integral into pieces. You can split it into 2 pieces, 3 pieces, 4 pieces, doesn't matter, but you're allowed to do that. Does that seem reasonable to everyone, that property? All right, how about property 8? Property 8 is a strange one. If you have a function f is even on the interval AB, or sorry, not AB, sorry, the interval negative A, positive A, then something. So let's try and draw a picture first. Does anybody remember from college algebra pre-cal what it means for a function to be even graphically, like in terms of its graph? What do even functions have to look like? No?
Is it where it can be reflected over the y-axis? It would look
Exactly.
pretty
All
much-
even functions are reflections of themselves over the y-axis. So one example of an even function is cosine. If I start drawing cosine like this, then if you reflect that over the y-axis, right, that is the function, right? It is itself. Like when you reflect it over, that is the function. Does that work for sine? If I take this sine here and I reflect it over the y-axis, that is not the sine function, right? Okay, so it doesn't work for sine, but it works for cosine. And then there's other functions that are even, like parabolas, right? X squared. If I graph x squared, the right side looks like this and the left side is a reflection of it over the y-axis. So if your function is even, all right, let me erase all this. If your function is even, and you're integrating from negative A to A, negative A to A, that's different. We're not going from A to B, but if we're going from negative A to A, and you know that whatever you do on the left-hand side, or sorry, right-hand side, the left-hand side is a reflection of that, then would you agree that the area here in yellow should be equal to the area here in green? Right? Those should be equal because it's an even function. So this property simply states that if you want to know the area from negative A to A, that all you'd really have to do is double the area from 0 to A. So if you could somehow figure out what the yellow part is, then doubling it would give you the area of the whole thing. And that may not seem like a very useful property. And I'll be honest, it really isn't that useful. I mean, we can use it, but you know, either way, we still have to find out what the antiderivative of the function is, either way. So, you're either going to plug in 0 and A and double the answer, or you're going to plug in negative A and A, right? It doesn't, like, computationally, it doesn't, we don't gain much from that. But property 9 is the one that's really kind of a nice one. So property 9 says, if our function is odd on the interval negative A to A, then what can we say about the area from negative A to A of this function? So can somebody take a guess as to what that would be? Maybe we should look at the graph. So if we have an odd function, what does it mean to be odd? Even meant it was a reflection over the y-axis, right? But what does it mean to be odd?
Reflection over the x-axis?
It's not quite just x. It's a combination. It's a reflection over y and then over x, which we call a reflection over the origin. So the sine function is a perfect example. Let me draw the sine function. This is what the sine function looks like, right? And then it goes the other way, like that. So what if I told you to just focus on the right side? What if I told you to reflect that over the y-axis first? Wouldn't you get this? Right, in black? But then I'd like for you to take that part in black and reflect it over the x-axis. So bring all that stuff down and bring all this stuff up. Then when you lay that down, it would lay right on top of the sine function. That makes sense? So it's a double reflection, over y, then over x. All odd functions have that property. So with that in mind, if I were going to take an odd function, like let's just say the sine function, if I were to just take that piece right there, stop here at A, want to know this area, and then go, remember the back side is a reflection, it goes like that. That's negative A, so it's that area. What can you tell me about those areas?
Equals 0.
Yeah, when you add them up, they'll cancel each other out. And so you should get 0 here. There's a problem in the homework, in one of the homework sections, that's something like this. It's like integral from -1 to 1. And then they give you like this crazy looking function. No, they give you like something like that. And they ask you what to evaluate this integral. And if you go try and do it, you won't be able to, because you can't find the antiderivative of this. Like there's nothing we have to find the antiderivative. So what you would have to realize on this is that this is an odd function. You'd have to say, oh, that's odd. And the reason you know it's odd is because x cubed, well, that's raised to an odd power, that's an odd function. X to the 7th is odd. X to the 5th is odd. The sine function is odd. Anytime you take odd functions and add them or multiply them or divide them, it stays odd. So you would know just by looking at this that the whole thing is odd. Then you know it goes from -1 to 1, which falls into this property negative A to A, so you know the answer to this is 0 and you don't have to do any work. But if you don't see that it's odd, then that's going to be a problem, because you're going to try and find an antiderivative and it's not going to happen. I'm not going to throw anything like that at you on a test. I just want you to be aware that that's one property. The thing that would tip you off is if these two limits of integration are like the same numbers, just one's negative, one's positive, you might be thinking, okay, wait a minute, hold on. I might be able to use the odd property here. Okay, any questions? All right, so in theory now, right, in theory, you could go back to all the homework assignments that you've done, every problem that you've done, and remember, when you were doing the problems, I always told you just ignore those numbers. Now you could go back and you could revisit those. You've already found the antiderivatives of these things, right? So now you can just go and use the evaluation theorem and plug in your endpoints and it's really just practicing plugging numbers into a function. That's all it is. So what I would suggest that you, where is it? I thought I had it here. Missing something? I thought there was an assignment here at the end. Where is it? Okay, hold on. I may have brought up the wrong. Give me a second. I thought there was an assignment at the end of this. There we go. So those pages, I'm just going to leave that up there for a second. Those pages, you can go back and look at all those pages and look at those problems. Those all have, you know, limits of integration on your integrals now, and you can just go back and just kind of plug in. On the test that's coming up on Wednesday, I'm not going to throw anything crazy at you. I'm going to have you do a problem. You find the antiderivative, you plug in the endpoints, you know, you're done. If you look at the review, which I'll put up here in a moment, I'll bring the review to the side so y'all can keep copying that down. Oh, shit, where did I go? Okay, so on the review, gotta find it first. Okay, there's the review. So you can see that on the review, there was 6 problems. There are 2 of them that are definite integrals. So, I mean, on the review, on the test, you know, just know that you could do it, that I could throw that in there. So like number 3, this is a problem where you have to do like some sort of, I don't know, partial fractions or something like that. But then at the very end, when you get your final answer, you got to go and plug in 1 and plug in 0 and then subtract the 2 answers. So I already worked that out, right? So we go and find the antiderivative, which is this part. And then, oh, did I not ever plug in? I didn't. Oh, I haven't finished that problem out. Because, oh yeah, I never finished the problem in the solutions. Oops. I have to plug in 1, I have to plug in 0. And I don't care how you give me that answer. You can give me it as a decimal or as an exact answer. It's totally up to you. Decimal would be fine. So just plug in 1, plug in 0, see what you get. Any questions? Can I get rid of this stuff here? All right. All right, so I want to show you something else before I proceed with anything. Get back to your notes for today. Okay, so when I started this whole idea of Riemann sums and everything else, we were motivated by the idea of trying to find the area under a circle, right? So that was a question that we were trying to answer, and we can actually answer that question now. All right, so we're going to go through this. This is actually really nice. We are going to prove that the area of a circle of radius r, lowercase r, is pi r squared. Okay, we're going to prove it. So the way we're going to do this is we are going to think about a circle So I'm going to draw myself a nice little circle here of radius r. So it hits there at r, it hits up here at r. And if we want to try to find the area of that, the only thing we know how to do right now is find the area underneath the curve, right? We can do that. If someone gives us a function that draws a curve, we should be able to find the area under it so long as we can find the antiderivative. So my first question to you is a circle a function? Like in the traditional sense of the idea of function, is a circle a function? Yes or
No,
Okay, why not?
because if you do the vertical line thing, you get 2 points on the same one.
Yeah, so a circle fails the vertical line test. And because it fails the vertical line test, it doesn't qualify as a traditional function of x, right? No go, fails vertical line test. But there is an equation for circles, right? We do have an equation that we learned somewhere, college algebra pre-cal, that gives us the equation of a circle. Does anyone remember the equation of a circle?
X squared plus y squared equals r squared.
Good. X squared plus y squared equals r squared. That's the equation of a circle. You might remember it this way. This might look like something you saw. This would have been in like conic sections and circles in pre-cal. This right here is the equation of a circle that is centered at the point HK and has a radius of r. That's your equation of it. Now, if you move that circle to the origin, in other words, you put the center of it at 0, 0, then it becomes this. Okay, so this is centered at 0. So that's just taking that formula, replacing h and k with 0, and then you get the one on the left, right? Okay, so that is not a function of x. We know it's not a function of x, fails the vertical line test. But I could still take this and solve it for y, right? I mean, algebraically, I could try and isolate y. I could subtract x squared on both sides. And then if I really wanted to, I could take the square root on both sides, right? Take the square root on the left, take the square root on the right. The thing is, I would have to do plus or minus. Anytime I take a square root, I have to do plus or minus. So y equals plus or minus square root of r squared minus x squared. So what this means is that that circle can be drawn if we're willing to look at it as 2 pieces. Okay, we have 2 pieces. The first one is this, y equals the square root of r squared minus x squared. The other piece is y equals negative square root of r squared minus x squared. So if we're willing to look at it as 2 different pieces, then each of those pieces by themselves would be a function. Now, if you don't believe this, I can just go to Desmos and graph it. I'll give you a moment there. What do you think is going to happen if I graph this one? What do you think it's going to draw in this circle? It's not going to draw the whole thing, right? What do you think it's going to draw?
Like a quarter of it?
Quarter of it? I heard someone say half of it, right? Let's see. Let's go to Desmos. Now I have to put in a number, okay? I have to put in a number for well, let's just see what happens here. I have to put in a number for the r. So I'm just doing a radius of, I don't know, 2 or something. So if I ask this to graph square root of, say, 4 minus x squared. Now, my scale is messed up. There's not an easy way to make this turn into a square. Boy, that doesn't look like a circle to me. Does it look like a circle to you? My proportions are off. All right, well, you'll just have to trust. I mean, you can tell it's 2 up, 2 over, 2 to the left, right? This is a circle. Unfortunately, it's not drawing it to scale. I wonder why. Hold on. See if there's something I can do here. Yeah, it is what it is. All right, now, if I draw the negative of that, negative square root of 4 minus x squared, I get the bottom half. Okay? So even though a circle by itself is not a function of x. If you're willing to split it into two pieces, you can draw the top and bottom, and each of those would be a function of x, wouldn't they? Each of those. So I'm going to ignore this one and just focus my attention on this one. And even better, I'm only going to focus my attention on that function right here in the first quadrant. Because if I can find the area that's in yellow, then I can just multiply that times 4, and that would give me the area of the whole thing, wouldn't it? Okay, so let's look at this. We have a function. It is now a function. F of x equals the square root of r squared minus x squared. That draws me this. Right? That draws me that. And I only want to find the area of this piece right here. So what would this definite integral look like then? The definite integral, where do I start? Where do I stop? So what's my left endpoint? What's my right endpoint?
0 to r.
0 to r. Okay, what am I finding the area of? So what is the function I'm finding the area under? Well, it's that function, right? Square root of r squared minus x squared dx. So if we can figure out what this is, then we're in business. So let's do some Jeopardy time. All right, why don't you think about how you would go about that, and then I'll come back in about a minute and see if anyone has an idea of how to go about that. So who has the approach?
Would it be using trig subs?
Trig sub, right? Remember, r is a constant. It's fixed. We don't know what it is, but it's a constant. So this would be a trig sub. And what would our trig sub be? X is equal to what?
R cosine theta.
R cosine theta. And then from there, we can get all the other information. The dx is r, is it cosine? Hold on.
I think
Is
it's
it sine?
r sine theta.
It's r sine theta, sorry. It's r sine theta. We could use cosine, but sine will work, I think. That's more consistent with what we were doing in class. The square root part will turn into r cosine theta. Okay, so we're making a trig substitution. Everywhere we see an x, we're going to replace it with r sine theta. The dx will be replaced with the derivative of that, which is r cosine theta d theta. And we already know by the formula that the square root, all that turns into r cosine theta. So now I'm going to redo this. Now, notice what I'm going to do. I'm going to not do the definite integral. I'm going to do the indefinite integral first. I'm going to go through all the work first here, get the antiderivative, then I'll come back and I'll plug in my two endpoints. So when I rewrite this integral, it will become integral, the square root turns into r cosine theta, the dx turns into r cosine theta d theta. Both those r's multiply together to get me r squared. I can pull that out of the integral because it's a constant, and inside I have cosine squared theta. And we've been here, right? We've crossed this bridge before. Cosine squared, we got to power reduce that, so a half is going to come out. Integral, and then we use that power reducing formula 1 plus cosine 2 theta d theta. Then this will become 1/2 r squared. It's time for antiderivatives now. So the antiderivative of 1 is theta. The antiderivative of cosine 2 theta is 1/2 sine 2 theta. Again, we've been here, right? Been here, done that. we also know that that sine 2 theta, we're going to have to use that double angle identity, turn that into 2 sine theta cosine theta. The 2's will cancel, or the 2.5 cancel. So I need to know what theta is, sine theta, and cosine theta. And this is where I go to my reference triangle, right? Getting all my information off of that right there. So with my reference triangle here, I'm using the fact that, let me divide both sides by r. X over r is sine theta. So this is x, this is r. This side would be square root of r squared minus x squared. That's theta right there. And that should be everything we need. This will become 1/2 r squared. Okay, so theta is actually arc sine of x over r, and then plus sine theta, which is x over r, and then cosine theta, which is the square root of r squared minus x squared over r, and then plus c. Are we good there? Okay, now let's go back to the definite integral. So we can take this now, we can plug in our antiderivative, which is 1/2 r squared arc sine of x over r plus x over r times square root of r squared minus x squared over r. That's my antiderivative evaluation bar from 0 to r. I'm going to plug in, get something. I'm going to move this down a little further. I'm going to get something here and then something here. Let's see what we get. Pretty sure I'm going to run out of room here. I can't move that. Okay, so let's plug in r. So I have 1/2 r squared. That's still there. Okay, when I plug in r for x, I get r over r, which is 1. So that becomes arc sine of 1. Okay, plus now I plug in for x, I replace it with r, so that's r over r again, that's 1. Times, now check out this part. When I plug in r right there for that x, I get r squared minus r squared, which is 0. Square root of 0 is 0, 0 over r is 0. So this is going to be a big fat 0 here, which is going to kill off just those two pieces. I'm still going to have the arc sine of 1 here out front, and I still have the 1/2 r squared in front of that. Is that clear to everyone? Okay, now let's plug in 0. So when we plug in 0, we get 1/2 r squared. Okay, so now I plug in 0 for x. 0 over r is 0, so I have arc sine of 0. And then when I plug in 0 for that x right there, it kills everything else off over there. So the only thing you have to figure out now is what is arc sine of 1 and what is arc sine of 0. So remember, arc sine is always going to spit out an angle. So when you say, let's do the second one first. If you say arc sine of 0, you're saying at what angle is the y coordinate, because we're talking about sine, on the unit circle, at what angle is the y coordinate 0? 0, right?
5.
Okay, and then on this one, this is saying, okay, where on the unit circle is the y coordinate 1? Straight up, right? Pi over 2. Okay, so I think we're there. This whole piece on the right-hand side is gone because that's just 0 plus 0, which is 0, and then you multiply that times 1/2 r squared. It's all gone. Over here, though, I'm out of room. I don't want to go to a new page, so I'm going to go up here. This is equal to 1/2 r squared times pi over 2, which is really, let's see, the half and the 2 can come together. That's 1/4 pi r squared. There we go. That's it. We just figured out that this area in here, right here in yellow, right? The area of that is 1/4 pi r squared, but that was only 1/4 of the whole circle, right? So if we multiply that times 4, we get pi r squared. And there it is. So we just proved that the area of a circle is pi r squared. All right, y'all like bonus problems, right? So I'm gonna let y'all work, because we're at a point right now where I don't want to start any new material. You have a test on Wednesday, all right? But I want to offer you a bonus question. And I'm gonna break y'all into groups, if that's okay with you all. All right, I'm gonna put you all in little breakout rooms. And here's what I want you to try and do. I'm gonna give you the first, because it's only 12:11. I'm gonna give you the first 5-10 minutes just to see if you can figure out the approach that you want to take for this. And then after that, I'll check with each group and see if y'all have the right approach. And then I want you to, I want to see if y'all can finish the problem out. So here's the idea. A cone. Okay, a cone. Hold on a second. No, hold on. I don't know if. Let's do it this way. We're not ready. We'll do that later. Okay, so anyone know what that's called?
Trapezoid.
A trapezoid, yeah. It's also called a frustrum. Okay, so just imagine what it is a triangle, okay? And what we're doing is we're taking some piece of that triangle like this, all right? Like that. Let's say that we know what the height of this is. And we know how long this piece is. So I'm gonna call that, I'll just call that A for simplicity. And let's call this B, all right? I would like to see if you can use a definite integral to come up with the area of that. Does that make sense? We could look it up. We could look up the area formula for a frustrum. Look, area of frustrum. Leave the page. Three-dimensional. We don't want three-dimensional. We'll do 2D. Let's see here. Yeah, so right here, A plus B over 2 times H is the area. If you know this, and you know this, and you know the height, okay? Then it's this. Now, I want you to do it with a definite integral. So somehow I want you could do, geometrically, you could just start cutting this into triangles and then I'm not asking you to do it geometrically. I'm asking you to see if you can come up with an integral that would give you the area of that. All right, so let's do some breakout rooms. Do it on separate paper, and whatever you do, you will turn in with your exam if you want it to count as bonus. All right, so on Wednesday, when you turn in your exam, you'll just turn this in with it. All right, so breakout rooms. And you're gonna have 3 to 4 people in each breakout room, all right? So go ahead and join the room that you're invited to, and then there's a way that you can ask me a question while you're in there, raise your hand as a group, and I'll come in and help you. Just be patient, because I might be talking to another group, all right?
Where is it?
What? The breakout room?
Yeah, is it just gonna be automatic or what?
It is there right now.
Oh, okay.
Yeah.
right one.
You're muted, Professor.
Every time I leave, it switches me to mute. Okay, so we're out of time, but that's a bonus question. You turn that work in with the exam next time. So when we get here on Wednesday, we're going to try and be quick in terms of me sending you the test, you copying it down quickly. You set up your space the same way you did for exam 1. I think it'll be a shorter process to get us started. Make sure you have all your formula sheets that you need. And then I'll be randomly picking a few of you for you to show me your sheets, and then we'll get started. You'll have the whole class time. You know, the scope of the test and the number of problems will be consistent with the review I gave you. But, you know, just make sure you're practicing, you know, everything. When I gave you all the review, I gave you all that second problem or no? No, I haven't. Let me check something real quick. I gave my other class another problem to do. Where was it? Okay, so this is problem 3. And problem 3 on the review, the denominator here factor, no, it doesn't factor, okay? You see this? This does not factor. And so, you know, you have to go through and follow the process here. You have a linear over an irreducible quadratic, so you do a basic u substitution, try and make the numerator look like the derivative of the u. We did this in class several times. And then when you get to this part over here, you have to complete the square, okay? What I would suggest is that you look back in our notes at a problem like this, where we have this denominator actually factors. So what you do is you go through a slightly different process, because if this factors, then you do not do all this. You just go to partial fraction decomposition. All right, so just make sure that I guess what I'm saying is, let's say that this were x squared minus x minus 6.
Sir, I don't know if we can see your screen.
Oh, dang it keeps doing that. I know you couldn't see my screen now. This is the third problem, right? So it's a linear over an irreducible quadratic. And so you have to go through this process, and then eventually you have to complete the square. What I'm saying is, I would suggest you work a problem like this also, where this is something like x squared minus x minus 6, where it does factor, and then your process is different, because you won't go through all of this. You'll do partial fractions. So you need to know, like during the test, like which way you're going to approach. If it's irreducible, you've got to do this. If it's reducible in factors, you go to your, find your A and your B. So I want you to have that practice before the test, because I don't want you to get to the test, spend 20 minutes doing something and realize, oh crap, I should have been doing something else. So I just felt like the review didn't have that type of problem on it. So I think the 5th one is another good example of that. See here on this 5th one, you do long division first, and then you're sitting here with this, and you have to factor the denominator. And this piece right here is not factorable. So you have to go through this ugly process. But if it was factorable, then you would do something else. So just be very aware of the difference between having a linear over an irreducible quadratic versus a linear over a reducible one, because the techniques are completely different for those two. All right. Guess that's it, yeah? See you on Wednesday. Get that second test done and move on. All righty, y'all have a good one. Bonus, you'll turn in at the, just turn it in with your work next time if you get it.
See you, Professor.
Thank you.
You and Zach.
Thanks, Professor. Have a good one.
You too.